Good day to all. My name is Rica Antalaya Jimenez, a BSE student. So my topic on chapter 5 is a multi-parameter optimization method. So before we tackle the multi-parameter optimization method, we will define what is multi-parameter optimization. So multi-parameter optimization is a method of solving complex designs problems mathematically that yields the best results possible. So optimization is a mathematical process that aims to find the best solution or design that satisfies a set of criteria or constraints. So the goal is to minimize the cost function, which takes into account all the factors important for the optimum design. So, to discover the best solution that satisfies the necessary performance criteria while minimizing the cost, the design parameters are modified iteratively using various optimization approaches. So, to add on, what is the meaning of multi-parameter optimization? Multi-parameter optimization is a finding the set of values for numerous variables, also referred to as parameters that maximize or minimize a particular object, is the process of multi-parameter optimization. This optimization approach is used to find the optimum course of actions for a particular issue in a variety of disciplines, including engineering, science, economics, and finance. So, next is what is multi-parameter optimization method? So, an optimization technique is included in a majority of commercial forward modeling computing codes. The length of the time needed for the solution of one model using various optimization procedures is a common cause of concern. Multi-parameter optimization techniques may be exceedingly slow if it takes a long time to achieve one solution, since the forward modeling routine must be used repeatedly until the best result is obtained. So most of the commercial codes for forward modeling computation contain an optimization approach. Then it is usual to have concerns about how long it take to solve a single model using different optimization technique. Since the forward modeling process must be applied repeatedly until the best outcome is found, multi-parameter techniques may be incredibly slow, and it takes a long time to aim or to arrive the one answer. So next is, in addition to computational effectiveness of the forward modeling codes, there's a great research interest in speeding up optimization routines convergence. So, in addition to forward modeling codes efficiency in terms of computation, there is a lot of research interest in accelerating the convergence of optimization routines. So by minimizing the cost of function in a design optimization problem, for example, the best set of parameter can be found through the use of optimization procedure, which is mathematical algorithms. So the next is, on the internet, or some of the internet, or the internet, some optimization codes are openly accessible. Both MATLAB's optimization toolbox and Microsoft Excel optimization functions use their respective solver boxes. So, for internet, MATLAB optimization toolbox and Microsoft Excel optimization are accessible and used for our respective boxes. So the next is, other methods are employed to shorten the computing time needed for multi-parameter analysis. Massively parallel computing techniques can be used to speed up computation if the software is licensed to operate across numerous computers. So using a perturbation technique, for the solution space is alternative strategy. Also, by the way, perturbation technique is a collection of analytical techniques for estimating nonlinear problems solution when exact solutions are not possible. So, little adjustments to the parameters that needed to optimize can still be made in this situation. But the rest of the solution space is either unchanged or just slightly altered. Due to the fact the entire forward model's solution is not necessary, this can reduce the amount of time needed for computing. So, to reduce the amount of time needed for multi-parameter analysis, to compute, other techniques are used. So, if the software is licensed to run across several machines, massively parallel computing techniques for the solution space. In this case, it is still possible to make small changes to the parameter that needed to optimize, but the rest of the solution space remains largely intact or just slightly changed. So this can decrease the amount of processing time required because the whole forward model solution is not required. So the next is one of the popular techniques is to reduce the solution space range where the cost function minimum is likely to discovered by using a coarse optimization grid and a small number of data points. So once found, the process can be performed a smaller grid with more precise bounds. The inherent risk is the situation it's that if the resolution is too coarse in the early stages of the investment, the global minimum value may be missed and an unsatisfactory solution will be found. So one of the common method is to use relatively coarse optimization grid and a space number of data points to the narrows and the solution space area where the cost function minimum is likely to be found. Then, after it is discovered, the procedure can be carried out on a smaller grid with more exact limits. So, this condition carries the inherent risk if the resolution is too rough in the early stages of the investments, the global minimum solve may be missed and acceptable solution may be found. Then the next is the ability to solve the issue when the more unknowns than the point of experimental measurements is one of the more intriguing possibilities with multi-parameter optimization. So this is achievable if the underlying mathematical theory is well defined and the fitting parameter is subject to well-defined limits and other restrictions. Such problems with unclear solution can be solved using optimization techniques, which is described in this chapter. Then, unlike the curve method is used in chapter 3, so where the number of data points is frequently significantly greater than the number of unknowns, this method does not employ the assumption. So one of the more exciting application of multi-parameter optimization is the capacity to handle problems where the number of unknowns exceeds the level of experimental observation. So this is possible if the underlying mathematical theory is clear and the fitting parameter is subject to clear-cut constraints. So using the optimization strategies discussed in this chapter, such issues and obvious answers can be solved. So unlike the chapter 3, the curve fitting method is used. So this method does not make the assumption that the number of data is always much more than the number of unknown. So the next is the examples of multi-parameter optimization method. So, the electromagnetic surface in impedance is a function of the depth and conductivity of horizontally stratified layers. In the simplest case of the single layer above the infinitely depth Earth half space, there are three unknowns: the conductivity of upper layer, the conductivity of a lower layer, and the depth of the lower layer. So the complex surface impedance measured at a single frequency only provides two measurements: the real and the imaginary parts of impedance. Given the depth of the penetration of the radiation and the limits on the conductivity, it is possible to reduce the three parameters from the complex surface impedance using optimization. So yes, it is possible to reduce the three parameters, which is the conductivity of the upper layer, the conductivity of the lower layer, and the depth of the lower layer. From the complex surface impedance using optimization, even though only two measurements, the real and the imaginary parts of the impedance, are available of single frequency. So this problem can be formulated as a nonlinear optimization problem where the objective function is different between the measured and the calculated complex surface impedance. And the unknown parameters are the conductivity of the upper layer, the conductivity of the lower layer, and the depth of the lower layer. So the optimization algorithm can use the depth of penetration of the radiation and the limits on the conductivity as constraints to the limits the search space of the unknown parameters. The optimization algorithm will try different combination of the unknown parameters and calculate the complex surface impedance for each combination using an appropriate electromagnetic model. The calculated complex surface impedance is compared with the measured complex surface impedance to evaluate the objective function. The algorithm iteratively updates the unknown parameters until the object function is minimized, which represents the best fit of the model of the measured data. So there is one example. I have one example also. So this environmental inputs, the to cost function. Select and read a published paper in your engineering discipline in which some form of optimization has been used. Review the published solution and comment on the other possible solution in which the environmental effects has been considered. So do you think that the published solution is optimal? So discuss your conclusion. So for me, I don't have the ability to browse or access published paper in specific engineering discipline. So however, I can provide the explanation of the concept of environmental inputs to the cost function and discuss some of possible approaches for incorporating environmental effects in optimization problems. So in engineering optimization problem, the cost of represents the object to be minimized and maximized subjects to constraint. In many cases, the function is defined based on the performance of system or process under the certain operating conditions. However, environmental factors can also significantly affect the performance of the system or process. So therefore, should be considered in a cost function. So, for example, in the design of the wind turbine, the cost of function could be defined as a total cost of the turbine over its lifetime, including installation, maintenance, and operation cost. So, however, the wind speed of turbulence intensity, which are environmental factors, can also affect the performance of reliability of the turbine. So therefore, it is important to incorporate these factors in the cost function to obtain an optimal design. One possible approach is incorporating environmental factors in the cost function is to use probabilistic models that consider the uncertain in the environment inputs. Monte Carlo simulation and other probabilistic methods can be used in generate a range of possible scenarios for the environmental and inputs. And the cost function can be evaluated for each scenario. So the results can be used to obtain statistical measure of the system's performance, such as the mean or the standard deviation. So another approach is to use multi-objective optimization, where both the system performance and the environmental impact are considered as the objective to be optimized simultaneously. This approach can be lead to trade-off between the two objectives, and the optimal solution is a set of Pareto optimal solution that represents the best compromise between the two objectives. In conclusion, the incorporation of environmental inputs in the cost function is important consideration in engineering optimization problem. There are several approaches that can be used depending on the specific problem and the available data. So it is important to carefully consider the environmental factors and their effects on the system or process in order to obtain the optimal design that is both efficient and sustainable. The published solution may or may not be optional depending on the specific problem and the assumption made in the model. So therefore, a thorough evaluation of assumptions and uncertainties in the model is necessary to determine the robustness and reliability of the solution. So that's all my topic about multi-parameter optimization, and thank you and have a nice day everyone.